Hello everyone. So let us start with the last module, that is finding the deflection of beams and frames by strain energy method. Okay, we have already studied the deflection of beams and frames by moment area method and conjugate beam method. Now those are the primitive methods. The new methods are nothing but these are called as the strain energy method, or they are also called as energy principles. Okay, so now in this energy methods, basically there are three types. So that is, one is strain energy method, it's also called as real work method. Next is Castigliano's theorem, and third one is the unit load method, or it's also called as virtual work method. So these are the only three methods used in energy methods. So energy methods are basically they are used to find out the solutions for mean specifically for indeterminate structures. So again, we know indeterminate structures are the structures wherein the unknown is always more than the equations of equilibrium. Okay, so now in this energy method, so first concept to understand is this external forces. Now, external forces are nothing but the forces which are acting on the body. So, load is an external force which is acting on the body. Now, this load is stored in the structure. Okay, and this load, when the load is applied on the structure, it is stored in the structure in the form of stress and strain. Stress, strain, and elastic deformation. So when you apply the load, to the beam, so before it bends, it undergoes stresses. Okay, so and that is nothing but the external forces. It will be when external force acts on the beam, it undergoes stress and elastic deformation. So in order to counteract this external force, there is an internal energy stored. Now this internal energy is nothing but the resistance offered by the structure. Now here, external load is the forces acting on the beam. Now to stop that external load, the structure will in turn have a internal energy, that is nothing but it will oppose the external energy. So always, in order to counteract both internal forces and external forces, so external forces will be always equal and opposite to that of the internal energy. Okay, so now we'll study what are this internal energy and what are the method used to find out this internal energy. So internal energy is nothing but this strain energy. So in strain energy, first method. So in strain energy, we'll be using equation here. Okay, so this is U is equal to integration of 0 to L is nothing but the length of the member, m square divided by 2EI. So m square is nothing but the moment, bending moment. Uh, E and I is nothing but the flexural rigidity, Young's modulus into moment of inertia. And this we are differentiating with respect to dx. Okay, we're integrating this and then with respect to dx. So that's the first method. Next, second method is Castellanos theorem. So Castellanos theorem, again, we'll be using two theorems to find out this. It's named after the person who has found out. Again, in all the three methods, you'll find deflection as well as the slope. Okay, deflection as well as the slope of the beams. Okay, so today we'll start the first method with the first method, that is Castigliano's theorem. So in Castigliano's theorem, there are two theorems. So first theorem, the second theorem. So in the first and second theorem in the first theorem, what is explained is whatever strain energy. Now strain energy is nothing but the internal energy stored in the member. When external forces act to stop that external force, the structure will have an internal energy. Now internal energy is nothing but strain energy, which is in turn called as stress. Okay, so now strain energy, if you partially differentiate the strain energy with respect to the load, then you'll get deflection. The same strain energy, if you partially differentiate with respect to moment, you'll get theta, that is slope. So strain energy, same strain energy with respect to load is deflection. Strain energy with respect to moment is slope. Okay, now it goes like this. If you want to find the deflection of any elastic structure based on the strain energy of the structure, so it states that in an elastic system, the first partial derivative of the strain energy of a structure with respect to any particular force equals to the deflection of a point of application of that force in the direction of its line of action. Okay, so if you differentiate u with respect to b, you'll get deflection. Now the same thing, now we have this, so we have the equation that strain energy is 0 to L m square divided by 2EI. Okay, now this is a strain energy equation, but we are interested in deflection. So if you want to find the partial derivative of this expressions, which gives the Castigliano's deflection rotation of the beam. So we'll be using these two equations. Because here, if you want to find delta deflection, so deflection using Castellanos theorem is, you want to find deflection, it is 0 to L partial derivatives, again, dou m by dou p into m over ei into dx. So if you differentiate moment with respect to the load into moment over ei, you'll get deflection. Similarly, theta 0 to L dou m by dou m dash into m over ei. Okay. All right. Of course, this proof is not usually asked, but anyhow, you should know this proof. It is simple. So first what we'll do is we'll take a simply support beam, and one is a hinge support and the roller support, and we'll treat it as a simply support beam. Then there are loads acting here, P1, P2 and so on up to Pn. Now I'll draw the deflected shape of the beam here. So again in the deflected shape of the beam, so below P1 there is Y1, below P2 Y2. Similarly, Pn, there is deflection is Yn. Now all are spaced at distance x1, y1, x2, y2, xn, yn, and the complete length is L. Okay. So now let us assume that the material obey Hooke's law. Okay. So this complete material will obey Hooke's law. Hooke's law. That is, when you apply load, the beam will bend, and when you remove the load, the beam will regain to its original shape. Okay, and there is principle of superposition acting here, and the work done by the external forces is P1, P2 and so on up to Pn. So now if you want to write the work done equation, so we have this work done equation. Now this work done is nothing but external force. External force work done is given by half of P1. So half of P1 x1 P1 into y1, only this force. This is external load and deflection, plus P2 Y2 plus half of P3 Y3 and so on, half of Pn Yn. Now work done by the external force is stored in the structure. So whatever force is applied, before it bends, it is stored in the structure. Okay. So that energy is nothing but it is called as strain energy of the structure. This energy is because of the external load. Then this energy is nothing but the energy stored in the structure. Okay, so now it is nothing but half of pi into y, means for any ith term, and there's ith deflection. Okay, so if any one load is increased by a differential amount, say dpi, if any one load here, if it is increased by a differential amount, so strain energy of the system will change. This is the strain energy will change by a small amount, that is dou u by dou pi into dpi. So dpi is external load. So now if the strain energy, the new strain energy because of the increase in the load is given by u strain energy plus dou u by dou pi into dpi, because this is the extra load, we are going to use it here. So u plus this parameter, so it is now u plus, again differentiate this, so it is pi into dui plus half of dpi into dui. So now this is both are the derivatives. So we'll ignore this term because both are derivative into derivative is very small quantity. So we'll ignore that. So now we'll take U dash is equal to, now this is the new strain energy, is equal to U plus only this parameter will take. Okay, Pi into dyi. Okay, so now if we apply dpi in the first term and then p, we get, so when you apply this, you will only use this portion. So it is dpi into yi. Okay, so since the order of application of load is not important, so work done in both the cases must be equal and opposite. So we'll take this parameter first. Okay, so remember this portion. Okay, u plus dou u by dou pi into dpi is equal to this parameter u plus dpi yi. So if you cancel out these terms, okay, so dou u by dou pi is equal to yi. So differentiate, if you partial differentiate the strain energy with respect to the load, which is equal to the deflection. And similarly, this is the same thing is considered for moments, that is dou u by dou mi is equal to theta I. Okay. Okay, now this is important. This here, note, if the deflection component at a point where no point load is applied or applied load is not in that required direction, then a dummy load, which is nothing but an imaginary load, is applied at that point. And calculate the strain energy at the point, put the dummy load is equal to 0. Okay, so this note we'll be using further. Once we start solving the problems, I'll tell you. Okay, then Castigliano's second theorem is, it states that in an elastic system, the partial derivative of complementary strain energy, U dash, of a structure with respect to any particular force equal to the deflection of the point of application of that force in the direction of the line of action. So it is even same thing. Now this time it is complementary strain energy. Complementary is the opposite of strain energy. So it is dou U star divided by dou Pn is equal to Yn. Again, if you differentiate U with respect to P, you'll get the deflection. Okay, we'll be using these problems. Okay, so let us start with the problem. So in this problem, they've asked to determine the deflection at load point using Castigliano's theorem. Okay, I've just clearly told, use it using the, find the deflection at the load point. So the load point here is at C. Okay, using Castigliano's theorem. Okay, so as usual, first, AB is a simply support beam, and there's a P load exactly at the center C, which is acting exactly at half of the distance L by 2 and L by 2 here. And okay, so what I'll do here is, first thing, as it is the most important thing here is, first thing you have to find the reactions. So it is a simply support beam in which the load is acting exactly the center. So this downward load gets equally distributed to the left and right because it is symmetrical. So downward force should be equal to the upward forces. So the upward forces is P by 2 and P by 2. Okay. So now, once you draw this diagram, find the reactions RA and RB. So RA and RB, RA is P by 2, RB is P by 2. Okay. Now, consider a section XX at a distance X from left hand. So what we'll do, we'll cut the section here and we'll measure this distance as X from end A. So now, due to this symmetry, it's symmetrical. So what I'll do is, I'll take only portion AC. So whatever bending moment I found out in portion AC, it is equal and opposite. It is same as that of BC. So now due to symmetry, so I'll consider only portion AC. So at X is equal to, so now the limit is 0 to L, 0 to L by 2. So now I found the reactions RA and RB, P by 2. Okay, so bending moment in the section XX. Now I've cut the section here. I've cut the section here and okay, so the bending moment at section XX is given by mx. So we'll cut the section here. So I'll see to the left side. So to the left side, there is only one force. So it is left side, it is going clockwise. So it is positive. So it is P by 2 into X. Okay, there's only force. So this is bending moment, P by 2 into X. Now, according to the formula, now we have the formula here, delta C is equal to 0 to L, integration of 0 to L, M over EI, dou M by dou P into dx. Dou M by dou P into dx. Okay, so what I'll do is first I founded the moment, so I'll write this moment here. Then I have to differentiate this moment with respect to P. So what I'll do, dou M by dou P. So I'll solve this here separately. Calculate dou M by dou P. So dou by dou P, I'll write it here. M is nothing but the moment which I founded here. So the moment here is P by 2 into X. So I've written here P by 2. So dou by dou P, I'll leave it as it is. And only the moment, whatever M is there here, this moment I'm going to write here. So now I have to differentiate. Okay, now how to differentiate is this? It's very simple. Now just check this out. This is dou P and this is dou P. So this dou P and dou P will cancel. So what is left is X by 2. So X by 2 I'm going to write here. Okay. Once again, how to solve this is dou, first write this dou by dou P aside. Then whatever moment is there from here, write it here. So this is dou P and dou P. Just cancel this. So you're left with X by 2. So X by 2. Alright. So now calculate the deflection at C. That is at the load point. So apply Castigliano's theorem now. So apply Castigliano's theorem for the entire beam. So we are going to take this complete beam. So it is like we have considered moment only in portion AC. In BC it is just same. So what I'll do here, apply the Castigliano's theorem for the entire beam, that is 2 times delta C. So whatever delta I'll get here, if I multiply it by twice, then it will be applicable for the entire beam. So now delta C is equal to, first delta C, load point is nothing but C. So delta C is equal to 0 to L M over EI into dou M by dou P into dx. Okay, so now because it is used for the entire beam, so I'll multiply this 2 times. So 2 into dou integration 0 to, okay, now let's check the limit because it is only AC. Now AC span is L by 2. It is 0 to L by 2 M over EI into dou M by dou P into dx. Now we'll substitute these values. So 0 to L by 2, M is what we have found out here, that is P by 2 into X, and over EI I'm going to write it as it is. Then dou M by dou P, I've already solved it here. Okay, so this is X by 2, so I've just put it X by 2 into dx. So now take the constant terms outside. So it is P by 2 EI, I've taken it out. So only X, we are going to integrate this only with respect to X here. So I'll keep only the X terms here. So it is 0 to L by 2 X square into dx. So P over 2 EI, I'm going to write it as it is. Integration of X square is X cube by 3, close the bracket, put the limits here, 0 to L by 2. Okay, so P over 2 EI, 3 again is a constant term, I'll take it out. So it becomes P over 6 EI. Now only this X is, in place of X, substitute L by 2, it's cube. So L by 2 cube is L cube by 8. So when you solve this, you'll get PL cube by 48 EI. So the answer is positive. So the positive answer indicates the load is acting downward. The deflection is acting downward. Show it here in the form of symbol. Okay. Okay. So the next problem is find the slope and deflection at the free end. In this free end, they have asked you to find both here. Slope, that is theta, deflection, delta at the free end. Okay. So it is it's a cantilever beam and there is a UDL throughout. Okay. The UDL is W per unit length. Okay. So they have to find both deflection and slope. So first let us find the deflection. Okay. So see here, now we'll use that note. We've used here, there was a note here. If the deflection component at a point where no point load is applied or applied load is not in the required direction, then dummy load is to be added, and the dummy load is nothing but 0. Okay, now see here, if slope and deflection in the free end. Free end here is B. So at B, there is a UDL acting, but not a point load. So, but our main intention is to find the deflection at B. So, if you want to find deflection at B, there has to be a point load. Okay, there has to be a load here, point load, more specifically a point load. But here there is no point load, there is a UDL at B. So what we'll do here is, because we want to find the vertical deflection at B, but there is no point load, so what we'll do here, we'll induce a point load. We'll apply a dummy point load. So here you can see here P is a load, it's a dummy point load. So to find vertical deflection at the free end, we need to apply a dummy point load P at B. So now let x be the distance from B. Let x be the distance from B, and we'll consider the complete, because the cantilever will always start at from the free end. Okay, we'll cut the section, we'll find the moment from the free end. And so the limit is 0 to L. Okay, so first let us calculate the deflection. So to calculate deflection, first let the consider the section. We'll cut the section here, and then we'll apply a point load. Then to the right side of the section, there are two loads acting. Okay, first we'll find the moment. Okay, to find this moment, to keep things simple, what we'll do, clockwise positive, anti-clockwise negative. So mx, okay, mx here would be p into x. Okay, you can see here, it's going like this clockwise, p into x plus w into x by 2. W is UDL, so w into x by 2. So this is a moment. Now we to apply it in the formula, we need to differentiate this. So dou m by dou p. So differentiate m with respect. So dou m by dou p. Only this you have to differentiate. So what I'll do here is here dou by dou p as it is. Write it as it is. Only the moment put it in the bracket. So it is p into x plus wx square by 2. Okay. Now how to solve this is, see here there is no p in it. Okay. So leave this. Then only take this parameter dou px by dou p. So what I'll do here, dou p by dou p I'll cancel. Only I'm left with this x term here. So x is the dou m by dou p. Okay. Next, calculate the deflection at the free end. Now to calculate the deflection at the free end, I've calculated both mx also, dou m by dou p. So now deflection using Castellanos theorem is delta b is equal to 0 to L m over ei dou m by dou p into dx. Okay, so it is 0 to L. Okay, 1 over ei, I'll take it outside. Okay, 1 over. I'll put the value of m. M is nothing but px plus wx square by 2. M is px into wx square by 2 is m into dou m by dou p. Dou m by dou p is x into dx. Okay, so 1 over ei, I'll take it outside. Then now I'll put it in the brackets. So it is 0 to L, complete length we are taking. So 0 to L, px square plus wx square by 2. Okay, I'll multiply this. So px square plus wx cube by 2 into dx. Okay, now we know that p is a dummy load. So p is a dummy load. So put p is equal to 0. So if I put this p is equal to 0, so this term is gone. So it is 1 over ei. So wx cube by 2 into dx. So now let's solve this. So w by 2 ei is a constant. I'll take it out. So x cube becomes x raised to 4 divided by 4, 0 to L. So it is now L raised to 4 divided by 8 ei. Here's the answer. So this is the deflection of the beam, simply support the beam when subjected to a point load with the UDL. So it's a UDL. Because there is no point load, we have deliberately induced a point load. Okay. Now, similarly, in the same case, they have asked us to find the slope at the free end. Now we have to find the slope at the free end in this portion. Slope at the free end. Now, if you want to find the slope at the free end, that is rotation, again, there is no rotation, no moment acting. So because there is no rotation, no moment acting here, so what we'll do here is we'll induce a dummy moment, like how we induced a dummy load at B. Similarly, to find the slope at the free end B, we'll induce a dummy load, dummy moment here. Okay, dummy moment at the free end, that is P. See here, again, this force is acting downward. UDL is trying to push the beam downward. To stop that, there is a UDL, this is a point load, sorry, the dummy load moment is acting upward like this. Okay, that's how we need to put this. External is trying to push the beam downward. Dummy moment is trying to push the beam upward. Okay, so again, I'll name this as P only. Okay, so let's calculate the moment here. So when you calculate the moment, it is same. Moment is equal to P. Okay, clockwise all positive and clockwise negative. So P into, so only P, clockwise rotation. So only P plus W into X by 2. Only this portion I'll consider, cut section. Then calculate dou M by dou P. So calculate dou M by dou P, with respect to P. So dou M by dou P with respect to P is, again as usual, dou by dou P, write as it is. Open the bracket, whatever M value is there, put it back here. Okay, which is equal to 1. Okay, now calculate the slope at the free end. So we have found out both here. M also we have calculated. Okay, now see here, when you put this bracket, there is no P in this. No P, so don't consider this. So dou P by dou P. So this has P in it. So dou P by dou P, this both will cancel. So dou P by dou P is nothing but 1. So calculate the slope at the free end. So when you calculate the slope at the free end, so as usual, theta, we apply the Castigliano's theorem, everything remains the same. Okay, the formula also will be same because we already put a moment here. The moment load is moment, we are used as P only. So we'll use the same formula. Okay, so apply Castigliano's theorem, that is theta B is equal to 0 to L M over EI dou M by dou P into dx. So 1 over EI M, we'll use the moment here, M, P plus WX square by 2 M, dou M by dou P, we have solved it, it is 1 into dx. Now we know that P is the dummy moment. Okay, so dummy moment P is equal to 0. So 1 over EI, this P will make it 0. So it is, you're left with WX square by 2 into dx. So solve this, you'll get WX square. So W by 2 EI, I'll take it out. So it is 0 to L, x square into dx. So integrate this. So W over 2 EI, x cube by 3, 0 to L. Okay. So theta B is equal to WL cube by 6 EI. Answer is positive. That means it is a clockwise rotation. Okay. So in this problem, we have found out both. Deflection at B, this is portion, and rotation at B. So because there is no point load, we have put a dummy load P, and we have also put a dummy moment P. Okay. So in the third type of problem here, so you can see here, determine the deflections. They have only asked you to find deflection at the load point. Again, it is a simple beam, simply support beam, but this time the load is eccentric. So load is acting at a distance A from end A and B from end B. Okay, it's eccentric. Okay, now again it is eccentric. Again things will be same. Okay, now because there are two spans here, the previous problems it was symmetrical, but here because there is different span and different length, so what we'll do, we will use a table. Now if you use a table like this, things become simple. So again, as usual, find out, first thing, they've only asked to find deflection at the load point, means you have to find delta C at this point, delta C. So as usual, first find the reactions. Now because it is eccentric, we already know the reactions. So RA and RB. So RA is nothing but W into this length, WP by L. So RA is WB by L. Similarly RB at this point, W, which is the farther distance, is A. So it is WA by L. Okay. So you can remember this well. So reaction at A, if you want to find reaction at A, take the far distance. So W B by L, reaction at B, take again the far distance, W A by L. Okay, then you have to calculate the moment. Okay, now use this table like this. If you use this table like this, things become simple. Okay, first, portion, origin, limits, mx, ei, dou m by dou w. Okay, now see here, in this I'm using dou m by dou w. So w is nothing but the load. Here in the problem only they have given us w. So I'll not take dou m by dou p. Instead of p, I'll take this w. Both p and w are same. Sometimes you use w for point load, sometimes you use for p for point load, but both mean the same. Okay, so let's start with this. First, portion AC. So this is portion AC. Next portion is BC or CV. You can write it anyhow. Next, origin. For point AC, from this span AC, A is the origin. For BC, B is the origin. We measure like this. Always we measure from the ends of the support. Okay. Then limit. Limit for AC, 0 to A. Limit for BC, 0 to B. Okay, next, moment in AC. So if I cut this section here, I'll see only to the left side. Left side only one load. So what is the moment? WB by L into X. It is WBX by L. Okay, load into perpendicular distance. Similarly, in this span, if you consider this span, origin is B. So origin is B, right side. If I cut the section here now, I'll draw XX like this. I'll cut the section. So to the right side, only one force. WA by L into cut section X. So I've written it WA by L into X. Next, EI is common throughout. If it is not given, it is understood that EI is same throughout. So it is EI and EI for both the section. Okay, now dou M by dou W. So dou M. So we'll take this equation. Dou M by dou W. So it has W in it. So dou by here dou by dou W. Okay, dou W by dou W will cancel. So left with only B by L into X. So B by L into X. Similarly, this portion dou M by dou W. So this is W AX by L. So dou W will cancel. We're left with only AX by L. Written it here. Okay, so if you use this table, things become very simple. So next is apply the Castigliano's theorem. When you apply the Castigliano's theorem, again it is 0 to L, okay, M over EI into dou M by, what we used to use P earlier, now it becomes W. P and W are same, into dx. Okay, now what we'll do here is, this is the equation. Now because there are two different spans, so I'll write this twice. Okay, so first 0 to L becomes only the span, 0 to A. So integration 0 to A, M over EI, dou M by dou W into X. Similarly, the next span, 0 to B, M over EI into dou M by dou W into dx. First split this and write, and now we are going to use this. Okay, now say 0 to A. Instead of M, write moment, this WB by WBL, WB into X by L. So WB into X by L. Okay, this is moment. Then this is dou M by dou W. So it is BX by L into dx. Similarly, B, 0 to B, moment WA by L into X into AX by L into dx. Okay, so this becomes WB square by L square EI common. So take only X, put only the X, 0 to A, X square into dx. WA square by EI L square is 0 to B, X square into dx. Okay, only take the X terms. So then solve this. So WB square by L square EI, X square becomes X cube by 3, 0 to A, WA square by L square EI, X cube by 3, 0 to B. So now it becomes WB, instead of A, put this WA cube B square by 3 EIL square plus WA square B cube divided by 3 EIL square. So delta B is equal to, what I'll do here is, I'll take this common. So W A square B square So this is from here a square, from here b square. So you're left with a plus b divided by 3ei into L square. So we know that a plus b is nothing but L. So I'll remove this, I'll substitute this with L. It is W a square b square. This L and L cancel. So it is 3ei L. So finally the deflection is W a square b square divided by 3ei L. And the answer is positive. So deflection is downward. Okay. So it's always better to use this table and draw when you have like this two different spans. So things become easy when you use this table. Okay, that's it for today. Thank you.